Assalamu alaikum. Welcome back to Mathematical Methods of Physics, lecture number 26. Before starting this lecture, let me review what we have studied in the last lecture. In the last lecture, we started series solution of the differential equations. Then we went on to study the Taylor series expansion of any function. And after that, we studied power series method. We haven't completed this topic, power series method, in the last lecture. We studied a couple of theorems where we can differentiate any power series term by term, a convergent power series term by term, and then we went on to solve a couple of examples to find the radius of convergence for the power series. So today we will be continuing with the same topic, series solution of the differential equations. So today's outline is power series method. We started this in the last lecture, so we will carry on with that. Ordinary and singular points of the differential equation, and then series solutions near ordinary points. So first of all, power series method. Let's start with the power series method. Example: solve the equation y prime plus 2y equal to 0 with the help of power series method. And because we developed some theorem for the power series in the last lecture, that when we assume that a solution has a power series solution, when a differential equation has a power series solution, then we assume that this power series is convergent in some interval. If it is convergent in some interval, then we can differentiate this series term by term. Alright, so if we consider y the solution of the differential equation in the form of a power series, then we can differentiate the above series and obtain y prime of x, and goes from 1 to infinity c n xn minus 1. Substituting the values of the last two equations in the given differential equation, because this is just a first order ODE, I just need y and y prime. If I replace these two expressions in here, I will get this. This is y prime plus 2 times y equal to 0. Now, the problem is, here we have x to the power n, here we have x n minus 1. Similarly, n goes from 0 to infinity, this n goes from 1 to infinity. So how can I combine these two expressions? So because we have different powers of x and different summation here, we cannot combine them right now. To compare coefficients, we need the general term in each sum to be the term containing x to the power n. So what we do is we shift the index of the summation in this term. Let's say in first terms, I want to make it x to the power n. So it means I can replace n minus 1 by n. Then this n and this n will become n plus 1, and n will start from 0 to infinity automatically. Alright, if this is confusing, then you can use some other index as well. Let's say n minus 1 equal to k. Then you get x to the power k. This will become k plus 1, ck plus 1, and k 0 to infinity. And here you don't need to replace anything, so just call n is equal to k. Then both will be the same. Here what we did is, we expanded this expression, n cn x n minus 1, which is this. Now here, if I start from 0, then n is equal to 0 will give me 1. So n plus 1, cn plus 1 x to the power n. If I start n from 0, then I have to write cn plus 1 x to the power n, and the coefficient will be n plus 1 as well. Now if I replace first expression by this one, then I have same series, almost same in the sense that x to the power is common and summation index is also same. Now I can write this in one series form, that summation n goes from 0 to infinity and xn is also common. So what we are left within is n plus 1 cn plus 1 plus 2 times cn, alright, equal to 0. Now this whole series will be equal to 0 if and only if all these coefficients inside these brackets will be equal to 0. For identity principle, we have this n plus 1 cn plus 1 plus 2 cn equal to 0 for all n greater than equal to 0. From here I can write cn plus 1 in terms of cn. This is a recurrence relation. The above equation is a recurrence relation for which we can successively compute C1, C2, C3 and so on. If you give me n is equal to 0, C1 in terms of C0, C1, C2, C2, C3, C3, C4. So I can recursively get all the coefficients back. But C0 will remain arbitrary because I cannot find C0 from here. So n equal to 0 implies C1 equal to minus 2 C0 over 1. N equal to 1 will give me C2 is equal to minus 2 C1 over 2. But C1 is 2 C0 by 1. So it will make it 2 square C0 by 1, 2. So this is 2 square C0 by 2 factorial. Similarly, C3 will give me minus 2 C2. This is not C1. This is 2 C2. C3 will be minus 2 C2 by n plus 1. Alright, so C2 is given by 2 square C0 by 2 factorial. 2 square times 2 will become 2 cube, and 3 times 2 factorial will become 3 factorial with a minus sign. So what is happening? Every time I'm getting one more power of 2, and factorial is also increased by 1 in each term, and minus plus is coming alternatively. So it means if I want to generalize and write any constant Cn, then it will be minus 1 to the power n, because n0 will give me plus, and 2 will give, n1 will give me minus, and 2 will give me plus, and 3 will give me minus. So this minus 1 to the power n takes care of this alternate minus sign. Now 2 to the power n, because C1 has 2 to the power 1, C2 has 2 square, C3 has 2 cube, so Cn will have 2 to the power n. And C0 is common in all the terms divided by n factorials, because 2 has 2 factorial, 3 has 3 factorial, n should have n factorial. So this is the general form of Cn. Now what will be your solution then? Your solution will be n goes from 0 to infinity, Cn xn. N goes from 0 to infinity, this is Cn. Now C0 is a constant, I can bring this constant outside, and you are left with 2 to the power n, x to the power n. I can write 2x to the power n. And minus 1 is also in n, so minus 2x to the power n. And if you recall, xn by n factorial was a Taylor series of e to the power x, e to the power x. But now x is replaced by minus 2x. So it means my solution should be e to the minus 2x. C0 e to the minus 2x. So this is my solution. C0 is arbitrary because it's a first order differential equation. In first order differential equation, I should have one arbitrary constant in my solution. I got that. This is an equation with a constant coefficients. If you want to find the solution directly, what you will get, it's a separable equation. Log of y should be equal to 2t minus 2x. And then if you take the anti-log, y should be equal to e to the minus 2x. So you see, we are getting the same solution from the power series method as well. So this authenticates the power series solution of the differential equation. It means it's a valid method. We can actually find the power series solution of the differential equation. And if your solution has exact equation, your power series solution will give you exactly that exact equation. All right? Note that the power series solution is the same as can be obtained by the separation of variables. All right. Then there is another example. Solve the equation x minus 3y prime plus 2y equal to 0 with the help of power series method. And again, it's very simple. I'm leaving this for you as an exercise. Again, on the same footsteps which we did in this example, it's a first order ODE. Similarly, this is also a first order ODE. Only difference is you need to multiply by x minus 3. All right. So this is a very simple example. You should be able to do it by yourself. I'm moving on to much complicated example, which is solve the equation x square y prime is equal to y minus x minus 1. So this is, again, x square is being multiplied by this. So we solve this equation with the help of power series method. Also discuss the convergence of the series. So if we write the power series in x, n goes from 0 to infinity, Cn xn, and again we are assuming that this is convergent in some interval. Differentiating the above series, we get this one and replace it in your equation. Y prime is replaced by this expression, y is replaced by this expression. Now again here, I need to multiply this x square inside. So if I multiply x square inside, it will become xn plus 1, n plus 1, right? So this is what I get. Now from here, n goes from 1 to infinity, xn plus 1. So first of all, I should combine these terms first, right? xn, xn. This is like n plus 1. So I should replace this n plus 1 by something else. Because of the two terms minus 1 and minus x on the right hand side, we need to split the first two terms c0 plus c1x of the series of the right expression. Because we already have constant and x. So just get the constant and x out of this expression. So n is equal to 0 gives you constant c0. N is equal to 1 gives you c1x, and then write the series from 2 to infinity cn xn. Because I wrote n0 and n1 separately, and now the series is from 2 to infinity. But on the left hand side, my series is from 1 to infinity, and this x to the power is also different than xn. If we also shift the index out on the left hand side by -1, how I will replace? N plus 1 will be replaced by n. Right? Because I'm shifting the index here. So n plus 1 should be replaced by this n. So you will get n minus 1 and n minus 1. This n and n will become n minus 1, this will become n, and this n will start from 2 to infinity now. And now you see we shifted the origin from the right, from the left side. Now we have the same summation on both terms, and x to the power n is also same. So now I can combine these two. If you combine these two, you will get Cn equal to n minus 1 Cn minus 1. So this is the last one, and C0 minus 1 should be equal to 0, and C1 minus 1 should be equal to 0. Because on the left hand side there is no constant and x terms. So if you compare the coefficients of constant, you will get C0 minus 1 equal to 0. So from there C0 will be equal to 1. And similarly C1 equal to 1 as well. And then after 2, 3, 4, you will get Cn equal to n minus 1, Cn minus 1. So this is a recurrence relation. So if I take n is equal to 2 here, C2 can be written as C1. C3 can be written as C2. C4 can be written as C3. And now I have the values, you can replace and get the answers. So C2 is 1 factorial, C3 is 2 factorial, and so on. So continuing in the same manner, we have Cn equal to n minus 1 factorial, because C2 is 1 factorial, C3 is 2 factorial, 1 less factorial. So if I write Cn, it should be equal to n minus 1 factorial, 1 less factorial. Therefore, the solution of the given differential equation is C0 is 1, C1 is 1, but from C2 onward it is n minus 1 factorial. Alright? So this is your solution in the series form. The question was also discuss the convergence of the series. For the convergence, I need to take this ratio, n minus 1 factorial divided by n minus 1 plus 1 factorial, which is n factorial. So if you simplify it, it's 1 over n, answer is 0. It means the radius of convergence is 0 here. So the series converges only for x equal to 0. So x is equal to 0 is of no interest. Alright, there should be some region where this series should be convergent, not at just one point. So remark is that the above differential equation does not have a convergence power series solution. This is a power series solution, but it's not convergent solution in some interval. So it means this differential equation does not have a convergent power series solution of this form. This example serves as a warning that the simple act of writing y is equal to Cn xn involves an assumption that may be false. You see, when we start writing this one, what we assume? We assume that y has this solution which is convergent in some open interval. And this assumption may be false. And in this example, it turns out to be false assumption, because at the end we saw that this solution is nowhere convergent. Alright, so we have to be careful in writing the solution. We can't just write the solution in the series form and start doing it. And if you don't, if you ignore this part, you will give us this answer that, okay, this is our answer, and you will be happy with that. Actually, you shouldn't be. The reason is, okay, you got the series solution, but this is not convergent, so this is of no use at all. It's not fruitful at all. So we have to stop and think something else for this type of equations. Alright, so this example serves as a warning. So it means we should define something else first before solving the differential equation. Alright, so what we do is we define ordinary and singular points of the differential equation. And this will tell you the story whether we can just go on and write the solution and solve it, or we have to do something else. All right? So first of all, what is the ordinary point? A point x is equal to a is called the ordinary point of the differential equation y double prime plus pxy prime plus qxy equal to 0. This is a second order differential equation in general form if both px and qx are analytic at x is equal to a. We defined in the last lecture, at the end, we defined what is the analyticity. If your function has a power series, convergent power series representation, then your function is analytic. And then we said, okay, if you have polynomials, they are analytic, so we don't have to worry about that. If they are rational, they are analytic as long as the denominator is non-zero. So this px and qx, they should be analytic. If they both are analytic at x is equal to a, your series is convergent. Your point x is equal to a is ordinary point. A point is, if a point is not an ordinary point, is called a singular point of the differential equation. All right? Now, here you see your px is 1 over x, and 1 over x is not analytic if x is 0. Right? If x is 0, it's not analytic. So x is equal to 0 is the singular point of the differential equation. All other points are ordinary points of the differential equation. If I take x is equal to 1, ordinary point. X is equal to 2, ordinary point. But x is equal to 0 is a singular point of this differential equation. And this is what happened in this example. If I write it in a standard form, x divided by x square, so 1 over x square y is singular at x is equal to 0. It means this is valid for ordinary points but not for the singular. All right? So this is how we define the ordinary and singular points of the differential equation. Remark. A quotient of analytical function is analytic whenever the denominator is non-zero. This is what we studied in the last lecture, so I am reminding it. Consider the differential equation ax, bx, cx. Now if this ax is 0, then it's a singular point because we have to divide it. This ax is being divided by bx. So if ax, bx and cx are analytic function, but ax is 0 somewhere, that point will become singular point. If a of a is not equal to 0, then the above equation is, for the above equation, x is equal to a is an ordinary point. If ax, bx, bx, cx are polynomials with no common factors, then x is equal to a is an ordinary point if and only if a of a is not equal to 0. The ordinary differential equation, this has two independent solutions on any open interval where the coefficients px, qx are continuous. If your px and qx are continuous functions here, then this will have two linearly independent solutions. Singular points need not be real numbers. Singular points can be non-real numbers as well. All right? They can be complex numbers as well. So singular points may be non-real numbers. So in this example, if you see this coefficient x is 0 at x is equal to 0. It means if I write this in a standard form, my px is sin x divided by x, which is not sin x divided by x, and this qx is x. If I divide x on the right hand side, I will get sin x by x and x square. The point x equal to 0 is an ordinary point of the above equation, despite the fact that ax is equal to x vanishes at x equal to 0. This x is 0 at x equal to 0, but still it is ordinary point. The reason is, if you divide this thing by x, your capital Px is sin x by x, and if you write 1 over x outside and write the series of sin x and now divide by x, now see, this is a convergent series. All right, this is a convergent series. It means Px can be written as a series solution. It means Px is analytic. So Px is analytic because the division by x yields a convergent power series. So still the series is convergent. But if I write cosine x here instead of sin x, then this will become a singular point because cosine has 1 here. So the first term will be 1 over x, and that is not a convergent series. All right, around x is equal to 0. Now, this example, the point x is equal to 0 is not an ordinary point of the differential equation, although the function px is analytic at the origin, but qx is not. This qx is not analytic. The reason is this is square root of x. Square root of x is not differentiable at x is equal to 0. If you take the derivative, the square root of x, the derivative is 1 over square root of x. 1 over square root of x is not defined at x equal to 0. It's not differentiable. If it is not differentiable, it is not analytic function. You cannot write this in terms of a power series representation. All right? So x is equal to 0 is not an ordinary point of the differential equation. Similarly here, log of x has no series in x. Log of x is not continuous when x goes to 0. So it means x is equal to 0 is a singular point. Here x is equal to 0 is a singular point. So in these both equations, x is equal to 0 is a singular point. All right. Determine the radius of convergence of a series solution of x square plus 9y double prime plus xy prime plus x square y is equal to 0 in powers of x. Repeat for a series in powers of x minus 4. Now you see, what is your p of x? P of x is x divided by x square plus 9. Q of x is x square divided by x square plus 9. Therefore, the singular points are, as we said, singular points need not to be real numbers. They can be imaginary numbers. So if I take x square plus 9 equal to 0, then x will become plus minus 3 iota. So plus minus 3 iota are the singular points. The distance in complex plane of each of these from 0 to 3, from 0 is 3. These 2 points have a distance of 3 from 0. So it means the radius of convergence is 3. So a series solution of the form has a radius of convergence at least 3. This is a result that if x is equal to 0 is an ordinary point, then the radius of convergence will be at least the distance of this ordinary point with the nearest singular point. That will be the radius of the convergence. So your series will have the radius of convergence at least 3. The reason is 3 is the distance from the ordinary point to the singular point. Then he said, what about the power series in x minus 4? 4 is also an ordinary point of this differential equation. But what is the distance of 4 from 3 iota? The distance of 4 from 3 iota is 5. So this series, if I write the series solution of this form, this will have a radius of convergence at least 5. All right. Let me emphasize this more by making a picture for you. Plus minus 3 iota our singular point, right? So in complex plane, this is plus 3 iota and this is minus 3 iota. The iota things will go with the y-axis. All right. If 0 is the origin, what is the distance? This distance is 3. This distance is 3. All right. So this implies that the ordinary point, the nearest to the nearest singular point distance is 3. So if I write series in x, this will converge from, this will converges with radius of convergence at least 3. All right. Now he said, what if you write the series solution of this form? So what if you write the series solution of this form? Cn x minus 4 to the power n. It means 4 is another ordinary point. Now the 4 is, now this is 3 iota, this is negative 3 iota. All right. And now your point is 4. This is the ordinary point 4, right? You are finding the solution about this ordinary point. Now you need the distance of this 4 from your singular point, this 5, and from this singular point as well, nearest singular point. They both are equidistant basically. So this distance is 3, this distance is 4. So using the Pythagoras theorem, you will get 3 square plus 4 square square root, which is 5. And similarly, this is also 5 because this distance is 3 and 4, 5. So it means this will converges with radius of convergence at least 5. In this case you will have radius 5, in this case you have radius 3. Alright, so that's how you can, this is another way of finding the radius of convergence if you are writing the series solution about an ordinary point. Alright, so series solution near ordinary points. First we will find the solutions of the differential equation in power series form near the ordinary point. Ordinary point is fine because we know that whenever we have an ordinary point, your series, usual series Cn xn will converge for some interval, at least with the radius positive. Alright, so that's no problem, but for singular points we have problems, and we will discuss that in next lecture. So let me solve one equation with around ordinary point. So find the general solution in the powers of x of the following equation, then find particular solution with y is equal to 4 and y prime equal to 1. Solutions near an ordinary point. Alright, so our equation is so first we need to find the solution in powers of x. Alright, clearly x is equal to 0 is an ordinary point of this differential equation. Ordinary point of differential equation 1. Right? So because at x equal to 0, this is not 0, so you can divide here and they will be analytic functions, no problem at all. So we assume the solution of the form y is equal to series n goes from 0 to infinity Cn xn, because we needed to find the series solution in x, in powers of x. Alright, so what will be the first derivative? N goes from 1 to infinity Cn n xn minus 1, and the second derivative will be n goes from 2 to infinity Cn n times n minus 1 xn minus 2. So now if I replace these three things in our 1, so therefore equation 1 gives x square minus 4 y double prime, and y double prime is 2 to infinity Cn n n minus 1 xn minus 2 plus 3x and y prime. Y prime is 1 to infinity Cn n xn minus 1 plus y, so y goes from 0 to infinity Cn xn equal to 0. Now you have to multiply this inside, so you will first x square will make it n is equal to 2 to infinity Cn n n minus 1 xn, because n minus 2 plus 2 is n xn, minus 4 times n goes from 2 to infinity Cn n n minus 1 xn minus 2. And now if I multiply this x inside, this will become n again, so plus 3 times n goes from 1 to infinity Cn n xn, and then plus n goes from 0 to infinity Cn x n is equal to 0. Alright, so now the problem is this is xn, it's fine, this is xn, it's fine. Here I need to replace this by n minus 2, and this is xn, it's fine as well. Alright, so these three are okay. This second term is n minus 2, so we need to do something with this one. Alright, so here in third term I can replace n minus 2 by k, let's say, or you may call it n again if you don't want. Otherwise, if you call it k, then you have to write k for every other expression as well. So this becomes n is equal to k plus 2, so it means this is k plus 2, this is k plus 2. So k plus 2, k plus 1. See k plus 2, k plus 2, k plus 1 xk. And if you want, and when n is 2, k is 0. So k will go from 0 to infinity. So you will have n goes from 2 to infinity, Cn n minus 1 xn minus 4 times k goes from 0 to infinity, ck plus 2, k plus 2, k plus 1. I am again writing it n because it's a summation index. Either change k in all of them or don't change k here. So I'm again replacing k by n. All right. So this is by changing this index from 2 to 0, I will have to add 2 in n. N plus 2, n plus 2, n plus 2 minus 1 is n plus 1, and xn plus 2 minus 2 is xn. All right, and then plus 3, 1 to infinity, Cn n xn, and plus n goes from 0 to infinity, Cn xn. Now xn is fine, each term has xn. All right, but summation index is still different. Summation index is still different. These both are starting from 0, but these are starting from 2 and 1. Now I cannot further change the index, because if I further change the index, this will not remain xn. This will not remain at xn. So what I can do is, these two have two more terms, because n is equal to 0 will give me constant, n1 will give me x, and n2 will give me x square. Rather here, n2, the first term is x square here. So what I can do is, I can open two terms here, I can open two terms here as well, and I can open one term here as well. So open 2, open 2, open 1, then every summation will start from 2 to infinity. All right. So what I can write is, if I write n is equal to 0 will give me C2 2 times 1 x0, and then plus n is equal to 1 will give me C3 3 times 2 x, and then I will write n goes from 2 to infinity, right? Because I have opened first two terms, so now I can write x from 2 to infinity. Now it's fine. Now you see this and this are same. And from here I need to open just one term. I need to open n is equal to 1 will give me C1 1 x1, and plus n goes from 2 to infinity. Again I opened first term and wrote the remaining one, and here again I need two terms to be opened. First term will give me C1, then plus C1x, and then n goes from 2 to infinity, Cn xn. And now I have all the summations xn 2 to infinity, xn 2 to infinity, xn 2 to infinity, and xn 2 to infinity. So now I can combine all those terms, but first I have to write the constants. This is a constant, minus 4 times 2 is minus 8c2 plus c naught. All right. So minus 8c2 plus c naught is a constant, and then the values of x. 6 4s are 24, so minus 24x, minus 24c3 plus 3c1, and 3c1 plus c1, 4c1. 4c1 minus 24c3. 4c1 minus 24c3 with x. And then I can write all the summation together now. 2 to infinity. From the first one I am getting this. n minus 1 Cn. From the second one you are getting n plus 2, n plus 1 Cn plus 2. Here Cn plus 2 is there. Cn plus 2 as well. So n plus 2. Alright, so you are getting C naught minus 8C2 plus 4C1 minus 24C3 x, and then n goes from 2 to infinity. If you combine them, you have n plus 2, n plus 1, Cn plus 2, and all others have Cn in it. So if you take Cn as common, you will get n square minus n plus n plus 1 Cn xn is equal to 0. This n and n are gone. So you are left with, so now this is equal to 0 if and only if your C0 minus 8C2 is equal to 0. So this implies that C2 is C0 by 8. Alright. Second term is 4C1 minus 24C3 is equal to 0. So this implies that C3 is equal to C1 over 6. Right? 4, 6 or 24. This is what you got. And then from here, then for n is equal to 2, for n greater than or equal to 2, you have Cn plus 2 equal to minus n square plus 1 Cn over n plus 2 n plus 1. This is the reconciliation you are getting. Here, if you see, this is 4 is being multiplied with this term and 3 is being multiplied with this term. So basically inside we are having 4 with this one and 3n with this one. Alright. So I'm getting 4 here and we are getting plus 3n. N square minus n plus 3n. Right? See, n square minus n plus 3n plus 1. So this will become n square plus 2n plus 1, which is n plus 1 square. This is what you are getting. So you are getting 4 in the denominator and n plus 1 square. Alright? And this is also with the minus sign. Minus 4. So this is plus 1. So this is the relation you got for your differential equation for n greater than or equal to 2. And now 1 square can be cancelled with this one. So you can finally write Cn plus 2 is equal to Cn over 4n plus 2, n plus 1 as well. N plus 1 Cn over n plus 2 for all n goes from 2, 3 and so on. Now if n is equal to 2, your C4 is equal to 3 C2 over 4 times 4. And what is C2? C2 is C0 by 8. So 3 by 4 square, C2 is C0 by 8. So this is you are getting 3 C0 by 8. If n is equal to 3, C5 is equal to 4C3 divided by 4 times 5. Right? So C3 is C2 by 6, C1 by 6. C3 is C1 by 6. So you got 4C1 by 4, 5, 6. Similarly, n is equal to 4 will give you C6 is equal to C6 is equal to 5C4 by 4 times 6. So that, and 4 times 6, and what is C4? C4 is 3 C0 by 4, 4, 8. So you got 3 times 5 C0 divided by 4, 4, 4 is 4 cube, and you get C6 and 8. 6 and 8, you can write 2 times 4 times 6, right? This is 2 times 4, 8 is 2 times 4, so I write 2, 4 and this 6, so I keep it separate. Now, and 6 will give you C8. First, let's deal with the even ones. This will give you 9, 8 will give you 7 C6 divided by 4 times n plus 2, which is 8. 7 by 4, 8, and C6 is 3, 5 C0 over 4 cube, 2, 4, 6. So that is 7, 5, 3 C0 divided by C0 divided by 4 cube, 4 to the power 4, and now 2, 4, 6 and 8. So you got 2, 4, 6, 8. This is what you are getting. So now we are getting some similarities. See? So if I continue and generalize for any even number, C2n. C2n will be, see, starts from 1, 3, 5, 7 and so on up to 2n minus 1 C0. You see, one less. For C6 we are getting 5. For C8 we are getting 7. So it means for C2n we will be getting 2n minus 1. One less. That's how we generalize, right? Divided by, now here 2n, it means n is 4 and you got 4 square. So it's half of it. For 6 you are getting 3. For 8 you are getting 4. Half of it. So for 2n you will be getting n. Half of 2n is n. And then 2, 4, 6, 8 and so on. So you will be getting 2, 4, 6, 8, so on. 2, 4, 6, 8, so on up to 2n. Because this is the same. For 6 it is 6. For 8 it is 8. So for 2n it is 2n. Alright. Now if you take this 2 as common factor, these are n factors. These are n factors. If you take 2 as common, you will get C0 divided by 4 to the power n. If you take 2 from each factor, you will get 2 to the power n. And each factor will be divided by 2, so you will be getting this up to n. This will become n factorial. So you got 1, 3, 5, so on up to 2n minus 1 C0 divided by 4 to the power n, 2 to the power n, and n factorial. What is 4 to the power n? This is 2 to the power 2n. So I can combine these two as well. So I can write finally C2n is 1, 3, 5, so on, 2n minus 1 C0 divided by 2 to the power 3n times n factorial. So this is for 2n, even functions, even coefficients. I'm done with that. Now what about odd coefficients? I got C1 to be equal to C1 by 6, C5 to be equal to this. So let's find C7, C8 and C9. C1 was, C3 was C1 by 6, C5 was 4, C3 by 4 times 5. This is what you have. So C3 is 4 C1 divided by 4, 5 and 6. C7 will come from n is equal to 5, will give me C6. So that will be 6 C5 divided by 4 times 7. And C5 is 6 times 4 C1, 4, 7 and 4, 5, 6. So this is what I am getting. Now n is equal to 7 will give me C9. C9 is 8 C7 over 4 times 9. So that will give me 8 by 4, 9. And C7 is 6, 4 C1 over 4, 7, 4, 5, 6. Alright, so I can write this as 2, 4, 6. I can write this as 2, 4, 6, 2, 4, 6 C1 divided by, 1, 4 got cancelled, you can write 2, 4, 6 and remaining is 4, 5, 6, 7, 9. 4 square, 5, 6, 7, 9. Or you can write, this is actually, 4, 6 is there, and if I multiply, divide by 2 here, 2, 2, this is 2, 4, 6 C1 divided by 4 square, 1, 4, 1, 4, and if you get 1, 2 times 3 here, then this is 2 times 2. So that will give you, actually every time you are getting 1, 4, 1, 4, 1, 4 in all these things. So let me do this like this. It's better if you write this C3. C3 is C1 by 6. So you can write 4, 3, C1 and 2. This is C1 by 6. 2 2s are 4 and 3 2s are 6. 2 and 4, 3. So here you will get 4 times 2 C1, 4, 5 and 4, 3. So 4 square and 5, 3. This will be better. Now if you write C1 as this one, C5 as this one, 4 times 2 C1, then this will become 4 times 2 C1, and it's 4, 7. So 4 square is already there. So you got 4 cube and 7, 5, 3. You got 7, 5. So you got 2, 4, 6 C1 over 4 cube and 7, 5, 3. All right. And now if you write this C1 in terms of this one, if you write 2, 4, 6 C1 over 4 cube 7, 5, 3, then you got 2, 4, 6, 8 C1, 2, 4, 6, 8 C1, and you got 4 to the power 4, and you got 9, 7, 5, 3, right? 9, 7, 5, 3, and so on. So this is so now if you generalize, you can write. So now if you generalize, you are seeing that for 7 we are stopping at 6, for 9 we are stopping at 8. So it means for C2n plus 1 you will be getting 2, 4, 6, so on up to 2n, because 1 less. 2, 4, 6 up to 2n, C1, and divided by 4 to the power 4. So this is 9 by 2 minus 1. So you got 2n plus 1. So you again got n. You got minus 1 by 2. So you got 4 to the power n again, because you have to take 1 off and then half it. 7 minus 1 by 2, 6 by 2, 3. 9 minus 1, 8 by 2, 4. And similarly, 2n minus 1 is 2n, divided by 2 is n. And 9, 7, 5. So this is 3, 5, 7, so on, 2n plus 1. This is what you are getting. All right. Now here it will become factorial, because you can take 2 as common, so 2 to the power n, 1, 2, 3, so on up to n, C1, divided by 4. 4 can be written as 2 to the power 2n, and 3, 5, 7 up to 2n plus 1. So you got n factorial C1 divided by 2 to the power n, because 2n minus n is 2n, and 3, 5, 7 up to 2n plus 1. So this is what you got for the odd coefficients. So you got even and odd coefficients separately. All right, so what will be the solution then? So therefore, the solution takes the form y is equal to sum as n goes from 0 to infinity, but now I have to write C2n x to the power 2n for odd coefficients, and C2n plus 1 x to the power 2n plus 1 for for even and odd coefficients. If you take n is equal to 0, you will get C0 plus C1x. If you take n is equal to 1, you will get C2x square plus C3x cube. So you are getting 2 at a time. All right. So now you know what your C2n is. So C2n is, we just found out that here, 1, 3, 5 up to 2n minus 1, 1, 3, 5 up to 2n minus 1, C0 divided by 2 to the power 3n and n factorial, x to the power 2n, x to the power 2n, and plus n goes from 0 to infinity, C2n plus 1, 2n plus 1 is this, n factorial C1 over 2 to the power n and 1, 3, 5 up to 2n minus 1, 2n plus 1 in this case, x to the power 2n plus 1. So this is what you got. All right. Now C0 is constant, you can bring it out. C1 is constant, you can bring it out. So what you can write, y of x is equal to C0 y1. y1 is a series solution, n goes from 0 to infinity, 1, 3, 5 up to 2n minus 1 by 2 to the power 3n n factorial, x to the power 2n. This is your one solution, plus C0 y2. y2 is n factorial divided by 2 to the power n and 135 up to 2n plus 1 in this case, and x to the power 2n plus 1. So you got two solutions, C0 y1 plus C1 y1. C0 and C1 are arbitrary. So you see, for second order differential equation around an ordinary point, I got two linearly independent solution, and of course their linear combination will be the general solution. Now the question was, find the particular solution corresponding to the given conditions. Now particular solution subject to y at 0 and y prime at 0 is equal to y0 is equal to 4 and y prime 0 is equal to 1. These were your conditions. So what your first condition will give you, y0 is equal to 4, implies that here you see n is equal to 0 gives you x to the power 1. It means in second solution all the terms contain x. So when x is equal to 0, this will become 0. And here n is equal to 0 gives you x to the power 0, 1. So first term is a constant here, and what is that? When n is equal to 0, you are starting from just 1. Over 2 to the power 0 is 1, n factorial is 1. So it's just 1. So you are getting C0, 1 plus all terms will become 0, and C2 times all terms become 0 is equal to 4. So this implies that C0 is equal to 4. This is one thing. Now y prime at 0 is equal to 1. This implies that, you see, in the first term you had 1 plus x to the powers, 1 plus x square plus so on. When you take the derivative, this 1 will become 0 and x square will become x. So all terms contain x in this expression. So C1 times 0 plus C2 times, you see, the first derivative, the first coefficient is C at n is equal to 0. You have 2 to the power 0 is 1, 1 times x. This is your first term, and second is x cube. When you take the derivative, it will become 1 plus x square and so on. So first term will be left. So first term will be left at 1 and all others will be 0. So this is 1, implies C2 is equal to 1. So therefore the particular solution is y of x is equal to C0 is 4. So 4 times 1 plus summation n goes from 1 to infinity, 1, 3, 5, so on, to n minus 1 over 2 to the power 3n n factorial x to the power 2n. I separated the first term because x to the power 0 is 1. I separated it. Plus, here first term is x and n goes from 1. If you don't write it like this, it's fine. No worries about that. N factorial 2 to the power n and 1, 3, 5, so on, up to 2n plus 1 and x to the power 2n plus 1. So this is your final particular solution. Alright, so that's how we can solve any differential equation about its ordinary point. About its ordinary point, you can just take this solution of the form Cnxn and start. Alright, and you won't have any problem. This series will be convergent for at least some interval. You can try it and try and see. This series will be convergent for some interval, so we have no worries at all. Alright, so that's how we find the solution about the ordinary point. So today we started with the power series method where we left off in the last lecture, and we actually solved a couple of examples. In one example we saw we got the valid solution, but in the second example we did not get the valid solution. So from there we got this classification of the points, ordinary and singular points for the differential equation. About the ordinary points, it's very easy to find the solution. It's a regular series solution where we can assume y to be Cn x to the power n and get the solution. That guarantees, ordinary point guarantees that this solution will converge for some interval. Alright, but for the singular solution we are not sure about that. So next time we will talk about solutions about the singular points. So till then, thank you so much for being with me throughout this lecture. I hope you understood this very well. I will see you in the next lecture. Till then, Allah Hafiz and Assalamu Alaikum.